So I'm going to be talking about SwiftSim.io, which at first glance may appear to people to be an attempt to replace YT, but I promise you that it is not that. What it is it's essentially a reference implementation of something that reads metadata from snapshots, is the kind of way that I think about it. And in SwiftSim.io and in the rest of the analysis pipeline for Swift simulations, we use unyt almost exclusively. Like, nobody is allowed to do any analysis unless it uses a unit array, because I'm so sick of like hearing from people about why this thing didn't work, and then you find out they did it in kiloparsecs instead of megaparsecs and things like this. So we've kind of mandated the use of unit across the board in terms of like the people who use Swift and the Swift data. So before I talk a bit more about SwiftSim.io, I'll talk about what Swift is. So Swift is a particle-based simulation code. It's similar to Gadget, but it uses kind of more modern technologies, and it's designed to be very modular from the beginning. And on the right is what Matt was asking about. This is using a new color map. So I also have a side project where I have Matplotlib color maps that are made to look like all of the Taylor Swift album covers, as we are Swift simulation. So this is for the new Evermore album that just came out today. So this was an overnight press release. Yes. So, okay, Swift, what does a Swift simulation look like? So people who, thankfully the talk before mine talked a lot about Halo catalogs and trees and things like this. So that's very useful. But essentially what we want to do is take some cosmological parameters and parameters in like a model that thinks about galaxy formation and put them through this generator that turns those like 10 bytes of data into petabytes of data, and then turn all of that data back into kilobytes of data at the end, which is the plots that come out the other side. And if we focus in on this analysis pipeline, this is the challenge that that YT is supposed to solve, right? So you take your snapshots and your Halo catalogs and some other data, and you put it all together, and you transform everything to figures, and then you can do your analysis that way. But there are some things that YT can't do, and there are some things that were difficult for us to integrate within YT, which is where the whole SwiftSim.io and our own kind of to the side analysis pipeline came about. But the thing that can do all of this is unyt. So we took what we saw as the best part of YT in an attempt to keep things as consistent as possible, and started building things on that to just kind of see how far we got. And then this is where our kind of slightly separate analysis pipeline has come from. So the key challenge that we were trying to solve when we were looking at the start of the Swift project for like, how are we going to do our analysis with the data that comes out of this, was how do you deal with modularity? So I can run a cosmological galaxy formation simulation with Swift, right? But the snapshot that comes out of the end of Swift, you have no idea what's going to be in it as an analysis package, because Swift is very modular. So what I can do in Swift is I can take the stars from Eagle, and I can mix them with the chemistry from Grackle, and I can mix that with some AGN from a different model. And what that means is that there's going to be different things in the snapshots every time you run it. Now, within Swift itself, we handle this high level of modularity by essentially writing all of the physics as extensions to the main code, and they all conform to the same API. But when you get to the output side, you also need that same level of modularity and understanding of what could be in there. And it then becomes very difficult to hard code things in the output analysis library of like, I know that there's going to be helium abundances in the output of the simulation, because there might not be, and they might be in a different place. And of course, this is one of the challenges that YT is supposed to solve, but I think the way that it's structured at the moment is it's like this type of simulation suite outputs this type of file, this type of simulation suite outputs this type of file. But because Swift in itself is so diverse, that's a difficult challenge to solve within YT itself. So the way that we handle this within Swift is by outputting a huge amount of metadata along with all of the particle data every time we write a snapshot. So what I'm showing here is just the output of H5 glance on one array in our output. So we include every single piece of metadata that anyone could ever think about in the output for every single array. And so the file format is completely self-describing. Even if I want to know what this field is, we also store on the output side a full description of what the field is. And if there's anything weird, we also describe that there. So one of the fields is like the time differential of the velocity divergence field. And there's a whole paragraph that gets output every time we write a snapshot, because the snapshot's going to be terabytes anyway. So you might as well write out, you know, a kilobyte of text to describe exactly what that means. So this is where I get to the point where I say SwiftSim.io is really kind of like a metadata processing machine and a reference implementation for reading the metadata out of Swift and doing useful things with it. So what Swift does is it takes all of the metadata in the Swift snapshot itself and then uses that to figure out what's in there, basically, and present that to the user. And then after that point, in some ways, the way that you access the data is quite similar to YT. So here I show something that a lot of people are familiar with, but with SwiftSim.io instead of YT. So we load the data in, which is just the call. So like in YT, we only read in the metadata in. But because that metadata is so important, that also is required to like set up the entire object hierarchy of how you would even go about reading the data. Because we don't build any assumptions in, apart from, I think the only piece of hard-coded metadata is that part type 0 is gas. And then everything else is completely determined from the file. So here, if I look at data.gas.element mass fractions, in the snapshot, that's an n particle by n array, where n is the number of elements you store. But because there are so many chemistry implementations, you may store 10, you may store 100, you may store 5 elements. And then there's additional metadata that tells you what each of those columns is. And then when you want to access the data, you do lazy loading like you do in YT, where you just select out a little piece of that array, and then you stick it in a unit array. So this is where unit comes in. So like I said, every time you load particle data from SwiftSim.io, it loads as unit data. And the other one thing that I found difficult in YT was visualization. I already spoke a short bit to Matt about this earlier. So partially because I wanted to try some new things with SPH projection, which we do, and partially because I wanted a different interface to visualization, we also added a small visualization package to SwiftSim.io. And this is very different to the way that the YT visualization works. So we load the data in a similar way, but the data transforms to take your snapshot to picture are quite different. So here it's a function that you call on your data. So you say, function, here is my data, please get me a grid. And all I wanted was the grid. And so the grid that comes out is a unit grid that has the correct units and things. But what this means is if I want to make a movie, I don't need to write out 100 PNGs and then stitch them together. And if I want to do a multi-grid plot of multiple things and lots of things like this, it's very easy to take this grid of data and then put it on the, put it into some matplotlib plot or feed it into func animation. And none of this is really supposed to be a, criticism of YT. I think it's just us trying to show that we did things slightly differently. And then the picture that comes out of that is this one, which is the 1989 Taylor Swift color map. So there's another one of these later on in the presentation. Okay, the other nice thing that we have is all of our statistics files, which track things like the total stellar mass in the universe, the star formation rate history of the universe, and things like this. These are also unit aware. So they're CSV files, but they include additional metadata so that we can read out the units and stick everything in unit arrays again. So now we have snapshots and log files that are unit aware. The other kind of key part of it, like a cosmological and galaxy information suite, is Halo catalogs. And I remember very specifically someone coming to me and saying, I want all of the plots. Now, the interesting thing about Halo catalog plots is that every Halo catalog plot that anyone has ever made, I can guarantee fits into like one of 3 categories. So you want to make a mass function, you want to make a scatter plot with a median line, or you want to make a 2D histogram with a median line on it. And if you can think of a different type of
you got about 5 minutes till the end of your slot, and then 5 more for Q&A.
Okay, great. I think, yeah, I'm nearly done. So those are the only types of plots that I think anyone has ever tried to make. And if anyone that disagrees with me, I'm happy to listen to you. But I don't think I've ever seen any paper that even has anything other than those two things in it. So the first thing, of course, that you have to do is you have to make your Halo data unit aware. So we use Velociraptor for our Halo finder. And we also have a similar system to SwiftSimIO that basically just reads out metadata and sticks it into a thing. And now here I've lazy loaded the stellar mass in 100 kiloparsec apertures out of this Halo catalog. And that's another unit array. And the final piece of the puzzle here is observational data. So if I am an astronomer who wants to write a paper, I usually want to take my simulation prediction for the stellar mass Halo mass relation and I want to stick some observational data on it. Now, we also made all of our observational data unit aware. So whenever anyone in the collaboration wants to add observational data to a plot, they write a small conversion script that takes like the CSV or the .dat or the binary format or whatever you get from whoever wrote the observational paper, and we convert that into an HGF5 file that contains a bunch of, you'll have guessed it again, unit metadata and cosmology metadata and metadata about the paper we got it from and the cosmology that the observers assumed and all of these things. So now I have all of my data from observations to the particle data to the Halo data in a consistent format. And as I said before, everyone who's ever made a Halo catalog plot knows that they're all exactly the same. So then I thought, well, we also don't even need to be able to write Halo catalog scripts to make plots out of that. You just need to describe what plot you want. So this also goes back to something that Matt was saying about his grammar to produce YT plots. The thing that we decided that would be most appropriate for something like that a little while ago was if you want to make a Halo catalog plot, you just ask what you want from it. And then everything else is handled internally. So on the right here, I have some YAML metadata that says, I want a stellar mass Halo mass plot with a scatter background. The legends in the lower right. On the horizontal axis, I want 200 crit masses. On the vertical axis, I want stellar masses of 100 kiloparsec apertures. I want a median line. And then at the bottom, you'll see observational data that says, put this MOSTA 2013 observational data on this plot as well. And because everything's unit aware, everything fits together. And so out of this piece of YAML, I get this plot with a nice caption and everything. And then I think, well, that's kind of it, really. I mean, everything's handled internally by the library. So you just take that YAML and the library knows that that field, the stellar mass in 100 kiloparsec apertures, should be formatted as the one on the vertical axis. On the horizontal axis, M200 crit is nicely formatted. And everything is all together within there. And then once you've got all of this infrastructure built up, you can start thinking about automation. So every time a Swift simulation dumps a snapshot, it can run Velociraptor, or we can run Velociraptor in process on the fly. So the Swift cosmological simulation will stop for a second. Velociraptor will be run on the data in memory. The Halo catalog will be dumped, and then it will start running again. Or we can run it after the snapshot has been dumped. But we can also run all of the scripts, all of the Halo plots, because they're all in a very consistent format. All of the units are the same. So you just pass this Swift pipeline, the config, which is basically a bunch of those YAML things. And you have to tell it what snapshot you want to use and things like that, because it's not, telepathic. And then you get out something like this, which is every plot. Well, so this is a small test version. This is like every plot that you could ever think of with redshift appropriate observational data on it. And this is all put together automatically by the Velociraptor system, the SwiftSimIO system, and the observational data system we have. It's all merged together from all of these disparate data sources into what you might think of as like a slightly dodgy HTML web page. But when you're using a HPC system, I think a slightly dodgy HTML web page is probably better than a like fancy, I don't know, you run a server on some piece of hardware and it serves all of this data to you. And yeah, all of this is open source. So all of the stuff that we took to turn all the observational data into the HDF5 files is all open source. The entire pipeline's open source. The configs that the collaboration uses for the production simulations and calibrating the production simulations is open source. And well, yeah, there's nothing that isn't open source here. And that's it. Thanks very much for having me speak. And like I said, this isn't meant to replace YT, and it's not saying that YT is bad. It's just something different that we've done. Yeah.
Well, I think I speak for everyone when I say, wow, that's pretty awesome. Thank you for sharing this. Okay, maybe I missed it. I was tweeting a bunch of compliments at various different times, but what is in the background here?
Oh, in this one, in this picture. Oh, so this is a SwiftSimIO data like thing that, like a image, a projected 2D image turned into a relief map with Matplotlib 3D. So each of these peaks is a galaxy. Yeah, it's just a fun visualization.
That's cool. I could.
It's the red color.
I'd like to build that. Oh, that's red. Oh, good. All right, we have a couple minutes for questions. Does anyone have any questions for Josh?
I don't know if I can, no.
Stephanie.
So I think this is as a non-developer, one of the things that I thought was difficult for plotting like particle codes was like for making projections was kind of dealing with your like smoothing length and stuff like that. Is that also all under the hood here? And is it easily dealt with via other codes? So like everything I think you've shown us is Eagle, but if I had some other particle code, you know, what would I need to do to use this?
So SwiftSimIO and everything is only designed to work with Swift data. That's why I said it's like, because it doesn't include any information on like what you should read, what's special, what's new. It's like basically just a metadata reader for the stuff that comes out of Swift. Mm-hmm. Now the projection, because everything comes out of Swift, and because we have all the metadata there, we know exactly what you use to run the simulation. We know exactly what SPH kernel you used. We know exactly what the smoothing lengths are and everything. And because it's all very tightly coupled like that, that's why making this projection image is just like basically like a one-liner. Mm-hmm. Because in this data object, all of the metadata is there about everything that was used to run the simulation, all of the outputs. Mm-hmm. You just go straight through from input to, you know, everything kind of working on the back end. And all of the projection stuff is handled kind of internally with an accelerated magic business. Yes. So in terms of SwiftSimIO being used by like people very widely, we don't expect it to kind of take over. In fact, I think it would probably make sense to replace the current Swift front end in YT with something that just calls SwiftSimIO, because that's probably an easier way to deal with keeping things up to date. Another problem as a front end maintainer working with YT is that every time you put something new into the code, you also have to go and edit YT and update your front end. Mm-hmm. And then keeping things updated, especially when you have a new code like Swift, is challenging because you're changing things all of the time. And that's yet another reason why we develop this kind of reference implementation, is because when we go and change things, it's very easy for us to change it and push out the changes and let everybody we know who uses it know that they need to update. Now things are settling down, I think it probably, yeah, like I said, I think it would make sense to use this to power the front end that we use in YT, because that way we don't need to worry about keeping that up to date.
Right.
Yeah.
Yeah, that's really interesting. So can I ask a follow-up?
Go ahead.
Okay, so then on a slightly similar note then is so SwiftSim.io seems very exciting, and one of the things that makes it really cool is that you have this extra, I think, extra metadata then in your Swift outputs. So, you know, this isn't that related to I guess your talk, but then, so do you think like the way forward for making everything kind of like smooth and easy, even in terms of like front ends and YT and stuff like that, is just people need to start putting, you know, all of this metadata information into their outputs, and it feels like that might not be a huge change and might make life a lot easier.
Yeah, I think that's definitely the way that things should probably start going. I mean, it seems a bit crazy when you're writing the simulation code to have like an output system that writes out all of this metadata, because you as the maintainer of the simulation code know exactly what, you know, units densities have, right? Like everyone knows that density is mass per length cubed, right? And everyone knows that the mass units used were 10 to the 10 solar masses, and the length units used were, I don't know, a megaparsec or whatever. Or maybe you even have some top level metadata that says those are the base units. But in terms of making stuff understandable to people who, like, you don't know who use your code, which is a big problem for Swift because it's kind of big open source, it's used by a lot of people now. It makes a lot of sense to me, at least, to spend the time when you're writing out the stuff, putting extra metadata in there, instead of going and writing that exact same metadata, but on the other side when you're writing the analysis package. Because then it's very easy to make a mistake. I mean, the reason that we started doing this is because well, not just me, but everyone kept making mistakes because, oh, I forgot that this was in kiloparsecs and not in megaparsecs, like I said at the start. And if everything's in the snapshot, and if everything's very tightly coupled through, and everything you get out is a unit-aware array, then you know there's not much space for mistakes. And then it enables stuff like, at the end, I showed the full automation of bringing everything together now that we know that all of the units are consistent and we know that everything's, you know, nicely kept together. I mean, I would have loved it back when I was using the original Eagle, which wasn't run with Swift, it was run with Gadget, if there was all of this extra metadata in there. There was some of it, but a lot of it was broken. And so now we've had a chance to go through and do everything again. It's less broken, I think.
Well, thanks.
Thanks.